Okay, integration by parts. This technique is useful for integrands involving the products of algebraic and transcendental functions. So something like x squared times e to the x, or an antiderivative of the natural log of x, which we have not done, or something more complicated like e to the x times the sine of x dx. Okay, so the rule, if u and v are functions of x and have continuous derivatives, then the antiderivative of u dv is u times v minus the integral of v times du. All right, so check this out. This is what the form looks like. U times dv. This is what its antiderivative is. So it's up to you to be able to pick what the u and the dv are. So there's a little rule for picking u in this order. Logarithmic functions, inverse trig functions, algebraic functions, trig functions, and then exponential functions. So when you are attempting to pick what u will equal, L-I-A-T-E, we go in that order. Then whatever remains in the integrand, that's what we'll pick for our dv. And once you see an example, it'll make a little more sense to you. All right, so the antiderivative of 4x divided by e to the x. All right, so first I'm going to write this as a product. So it'll be 4x times e to the negative x dx. All right, my little order for picking u. So I need to be able to determine from this u and dv. All right, so I need a function that I find the antiderivative to find v, and I need u that I'm going to then find the derivative of. Okay, so according to our little mnemonic device here, our u will be the algebraic expression 4x, which makes dv e to the negative x dx. Okay, so then from these pieces, I now find the derivative of u, so this would be 4 dx, and then I find the antiderivative of dv. Okay, the u substitution here, u would be negative x, which gives me a derivative of negative 1, so the antiderivative would be e to the negative x. We do not need the constant of integration when we're finding the value for v, or the expression for v. Okay, now the rule says this antiderivative, u times v minus v times du. So u times v minus the antiderivative of v times du. Okay, so just filling it in, u times v minus the antiderivative of v times du. So now let's clean this up. Negative 4x e to the negative x. I'm going to bring that negative out front and the 4. So now I'm just integrating e to the negative x. So now integration by parts, it still requires you to find an antiderivative, but the whole goal is to get the antiderivative to be more simple than what the original integrand was. So now we're just finding the antiderivative of e to the negative x, which is actually what we already did when we attempted to find v. So negative 4x e to the negative x plus 4. Again, just to write this out, your u substitution would be the exponent, negative x. That derivative is negative dx, so this would be negative e to the negative x plus c. All right, if we want to fix that up a little bit, we could take out a negative 4 e to the negative x. That would leave me with x plus 1 plus c. And there's your answer. All right, x to the 4th ln of x dx. Now let me say again, integration by parts is another technique. It doesn't replace U substitution. It doesn't replace fitting something into a trig antiderivative. So as you work on practice problems, you'll still have to use other techniques. I know this problem already is not going to be a U substitution. I'm multiplying x to the fourth and ln of x, so parts is what we'll set up. All right, so U, again, I'm going to pick my, or not my algebraic. Algebraic is after my logarithmic function, okay? And let me talk about that for a sec. If I put dv as the natural log of x, you can't integrate that function yet. By the end of this lesson, you will, but ln of x is going to have to be my u. Okay, so natural log of x, which makes du 1 over x. dv, therefore, will be x to the fourth dx, and that antiderivative x to the fifth over 5. Again, you do not need to have the plus c when you're finding what the value of v is. Okay. So now the antiderivative, u times v minus the antiderivative of v times du. And I should have dx in there. So it sets it up where the bounds match, so our variables are correct. X to the fifth ln of x over 5. Oh, sorry, guys. It's a 5. So now these will cancel. I'm going to take out my 1/5, and I have the antiderivative of x to the fourth dx. So now I'm only integrating using the power rule. X to the fifth ln of x over 5 minus 1/5 x to the fifth over 5 plus c. All right, if we want to factor out an x to the fifth divided by 25, 5 ln of x minus 1 plus c. For the antiderivative of 4 arc cosine of x. L-I-A-T-E. All right, so in the order for picking u, no logarithmic functions, but I do have an inverse trig function. So my u is going to be arc cosine of x, which makes my dv 4 dx. Okay, the derivative of arc cosine, -1 over the square root of 1 minus x squared. The antiderivative of 4 is just 4x. Okay, so by parts, u times v, cosine of x, minus the antiderivative of v times du. I keep forgetting to put that dx in there. Okay, 4x arc cosine of x. Take the 4 out. Now I have x divided by 1 minus x squared. So now again, you're still evaluating an integral. So to complete this problem, I'm going to have to do a u substitution there. So u would be 1 minus x squared, du negative 2x dx. So I bring a negative 2 out front. 4x arc cosine of x minus 2, and this would be the antiderivative of u to the negative 1/2. Minus 2, add 1 to the exponent, divide by the nu. 4x arc cosine of x minus 4 times the square root of 1 minus x squared plus c. So they're lengthy. You don't lose the need to find an integral. It, again, just gives us another tool. Okay, the tabular method. So when you have an integral set up in the form x to the n e a to the x to the n sine a of x, or x to the n cosine a to the x. And we're going to do this example, but if you had to integrate x squared cosine of x, you would have to do parts 2 times to evaluate this integral. When you have a function in the form x raised to some power, and then it has to be sine, cosine, or e because you can find those antiderivatives, then we can use this integration by tables. So the table is, we alternate signs, we pick u and list its derivatives, and then we pick v and its antiderivatives. Sorry, spent a lot of space over here. Okay. So to use the tabular method, we'll start here, and then you'll see how the other 2 columns will fall into place. All right, so the antiderivative of x squared times the cosine of x. So it fits that form. So I have my sines, I have u, and then I have dv. All right, the same parts that we need to pick when we're doing any integration by parts. My u is going to be my algebraic function. Okay, algebraic will always come before trig and exponential. So I list the derivatives of u. So derivative of x squared is 2x, then the derivative of 2x is 2, and then I list until I get to my derivative of 0. So my signs, I alternate signs, always starting with a positive sign. So positive, negative, positive, negative. And then from here, I find my dv. So then my dv is going to have to be cosine of x dx. So that other part that remained. So the antiderivative of cosine is sine of x. The antiderivative of sine is negative cosine. And the antiderivative of negative cosine is negative sine of x. Okay, so then the antiderivative is defined as, you pair the first sign with the first u, and then it gets paired with that value for dv. And I pair these, and I move down on dv, over, and here. So of course we won't put in the 0 at all. So then what's the antiderivative? Positive x squared times sine x, negative 2x times negative cosine of x, so plus 2x cosine x, positive 2 times negative sine x, so minus 2 sine x plus c. And we're done. Okay, let's see here. Let's do for homework. At least determine u and dv for this problem, and set up the integration by parts. Do not evaluate. Set up, but do not evaluate.